still 50 points a week for your journal check there. Hey, look at this, summer school for all. Hey, I plan on updating my YouTube channel there with playlists that sort of correspond to each of the chapters in the ACE Physics textbook. So for example, the waves physics spans 3 chapters, and so each one of the set of slides corresponds to a chapter. And so there's a chapter about waves, there's a chapter about superposition, there's a chapter about stationary waves. And so those sets of learning outcomes each correspond to a chapter. And so with this one here, this will be sort of 4 out of the 17 or so chapters that we like to cover throughout ACE Physics. And so I'm going to try to get as much of that done with worked example problems and other videos that sort of explain some more of the concepts there. And so you're all invited to attend some summer school with Dr. Schleith here. It's going to be focused on physics, but I'll also try to do more geared towards astronomy. Sort of stay tuned for that. I'll even get you all with a pop quiz when you least expect it. And if you're expecting one now, well, then I'm not going to get you with one, right? Because I'm going to get you when you least expect it. All right. So here's the ideas here about radioactivity. Here is one of the core standards. So this is like a state of Florida next generation science standard, physical science. It says explain and compare nuclear reactions, radioactive decay, fission and fusion, the energy changes associated with them, and their associated safety issues. It says identify the 3 main types of radioactive decay, alpha, beta, and gamma, and compare their properties, composition, mass, charge, and penetrating power. Explain the concept of half-life for an isotope. For example, C14 is used to determine the age of objects, and calculate the amount of a radioactive substance remaining after an integral number of half-lives have passed. Recognize that the energy released per gram of material is much larger in nuclear fusion or fission reactions than in chemical reactions due to the large amount of energy related to small amounts of mass by the equation E equals mc squared. So that is just one single standard from the state of Florida, and it's the one that is relevant to the ACE learning outcomes, which you see here. So whether you're taking physics honors or pre-ACE, if you're studying physics, the physics is the physics, and this is what we're going to kind of focus on related to a broader idea of radioactivity and an even broader idea of matter. So describe the nuclear model of the atom and the evidence for it, represent nuclides using their nucleon and proton numbers, use a simple Quark model to describe protons and neutrons, and appreciate that electrons and neutrinos are leptons, show an understanding of the nature and properties of alpha, beta, and gamma radiations. I'm going to really try to focus on these 5 learning outcomes. I'm not going to sort of get to everything that's included in the remarks here. There's an awful lot there. But indeed, you should have a good foundation to continue to sort of study this standard here. And we're going to mainly focus on, as we see here, the alpha, beta, and gamma radioactive decay, those 3 main types of radioactive decay. There's a lot of overlap there. All right, describe the nuclear model of the atom and the evidence for it. So if you remember the gold foil experiment, we usually refer to it in sort of chemistry classes. Sometimes they'll refer to that as the Rutherford's alpha scattering experiment. So a beam of alpha particles, which are positively charged, most of them go straight through. Most particles are undeflected. That's one conclusion. Some particles are scattered off by sort of a little angle. Okay, and very few particles are scattered at these sort of large angles, almost sort of bouncing back towards the source there. So those are sort of the 3 conclusions that were reached when Rutherford, bombarded this thin piece of gold foil with some alpha particles, which are just helium nuclei. What does that mean? Well, because most particles pass straight through, the atom consists of mainly empty space. Okay, there was no interaction, the alpha particles just passed clean through. Because some particles were deflected through a small angle, the atom contains a central positively charged nucleus. As those positively charged alpha particles came near the nucleus, those positive charges repelled, and so they were deflected at a shallow angle. So now we know that the atom contains a central positively charged nucleus due to that observation. And then the final observation that a few particles were deflected back towards the source at a very steep angle, the conclusion there is that the atom contains a small, dense central nucleus that contains most of the atom's mass. So if there was almost a head-on collision, then the really strong positive charges would repel and it would sort of turn that particle back around. And so that indicated that the the substance of the atom was contained in a very small, dense central nucleus. Right, and so that's the key idea with Rutherford's alpha scattering, or the gold foil experiment, suggesting that atoms have a nucleus, so the nuclear model for the atom, as opposed to some of the other models that you might have studied in your chemistry class when we kind of look at the history of atomic theory. Represent nuclides using their nucleon and proton numbers. All right, and so this is a nuclide symbol. It's got the element. I don't know if I should get myself a drawing tool here. Stand by, class. Let's see if I don't want to publish anything on my screen here. Let's see. Do I have a drawing tool? Get that one back up here. All right. Hopefully a drawing tool will come up and I can use that. All right. So the I'm not even sure if, for example, my cursor is captured on the screen recording software, but I know that this will. All right, so we've got the nucleon number. Remember, that's the number of nucleons. So that's how many particles are in the nucleus. So it's the number of neutrons plus protons. Okay. The atomic number is just the number of protons, right? And so this tells us the amount of positive charge. This number right here, the bottom number, the number of protons, or the atomic number, it identifies the chemical species. So anything with 3 protons is lithium. All right, and if there's 4 neutrons in there with those 3 positive charges, then it has a nucleon number of 7, right? And so that's the number of neutrons plus the number of protons. And all that information together is what we call a nuclide symbol, right? So represent nuclides using their nucleon and proton numbers. That's the idea there. Here's a chart of some nuclides. This has the first 8 elements up to oxygen, so you can see that there's some isotopes of hydrogen. We've got helium, different isotopes of helium, but anything with 2 protons is helium. So there's, helium-4 is the sort of typical. So you see sort of the most common isotopes there, sort of in red, with more rare isotopes on either side of that sort of red line that kind of goes sort of right there. Stand by. Right, so this sort of staircase line right here in red, that shows sort of the stable, the most stable isotopes. And so you can kind of see, I think they've got, this might be the half-life over here of these. Yeah, because carbon-14, you can see here, 5,730 years. And so that's the half-life. And so we can indeed tie it back to that standard, which I think specifically mentioned carbon-14. So it's telling us how much time it takes for half of that substance to decay. And so it's unstable, and it's going to undergo one of these sort of radioactive decay processes that we're about to just sort of briefly introduce. And let me sort of reemphasize that. These slides sort of give you an idea about what the learning objectives are and sort of give you some information. It's really up to you to kind of go through the reading and to kind of do some practice problems to really make sure you're mastering these learning objectives. And so, by going through the slides and transcribing notes, that's hopefully helpful to some students. But to really master these, you really got to kind of work with the material. All right, and so it looks like we see just a table of these nuclides here. The learning outcome is just to be able to, represent nuclides using their nucleon and proton numbers. And so here's just sort of one way where we see some of that information there. We have the number of neutrons and the number of protons, so we could grab sort of any one of these nuclides, any one of these isotopes off of this chart and write it as a nuclide symbol, right? We'd know that the nucleon number would just be the sum of the proton and the neutron number for any one of these. Let's just do this one right here, nitrogen 17. All right, so because it has 10 neutrons and 7 protons, so you can see anything with 7 protons is nitrogen, right? That's sort of what defines the chemical species, is the amount of positive charge, the number of protons. And so we would write its chemical symbol, N for nitrogen, and we'd write the number of protons, or the atomic number, down here, and then we'd write the nucleon number, which is the number of protons plus the number of neutrons, up here. And so that's an isotope of nitrogen. That's the nuclide symbol for nitrogen 17. Right? Most nitrogen in the universe is nitrogen 14. All right, and so here, 99.63. I don't know if that's maybe like the percent, sort of composition, because you can kind of see here like oxygen 16, 17, and 18. They've got 99.759, so 99% of the oxygen is oxygen 16, 0.037% is oxygen 17, 0.204% oxygen 18, and then here, sort of in blue, we see where we're given time units, that those must be the half-lives, and we can just kind of deduce that from, it's I'm familiar enough with the half-life of carbon-14 there, 5,730 years, because we use carbon-14 in radioactive dating. That's kind of what this standard, is about up here. Let's remind ourselves of that. Right, so here it says, explain the concept of half-life for an isotope. For example, carbon-14 is used to determine the age of objects. So let's kind of go back down to that chart then and consider that carbon-14. So this carbon-14, it says it's an isotope, right? Most of the carbon in the universe is this carbon-12 here, right? 98.89%. But, some amount of carbon in the universe is carbon-14. And so if we have, say, something that used to be alive, some carbon-based life form, there's probably some amount of the carbon that carbon-based life form would have in it is going to be carbon-14, but it's going to decay. So if we can sort of estimate how much carbon-14 should be in, say, a bone of a given size, and then when we measure the amount of carbon-14, we can sort of use this idea of radiocarbon dating to then age how old that fossil is based on how many half-lives, because the half-life of carbon-14 is so well known. And so that's just sort of a quick explanation about how they do radiocarbon dating. And for longer lived isotopes, we can age things that are much, much older. Because you can see, 5,730 years isn't very long when you're trying to look at things on, a geological time scale where, things could be hundreds of millions or even billions of years old. This chart only has up to oxygen, but uranium, on most periodic tables, they'll show that as a stable element, but its half-life is, I think, like 4 billion years or something, so it's pretty stable. But it technically does have a half-life of 4 billion years. All right, the next learning objective here is use a simple Quark model to describe protons and neutrons. So I'm going to dwell on this for too long. There's so much physics, sort of at work here, from quantum chromodynamics, quantum mechanics. When we start to think about the sort of science of the very small and nanotechnology applications of understanding nothing quite at this small of a scale, but this is the physics here is really awesome, and so we're just trying to use a simple Quark model to describe protons and neutrons. So let's think about why that's important. We know that matter is made up of protons and neutrons, right, and electrons, atoms, and so, but protons and neutrons, it was discovered, were not fundamental particles. They were made up of even more fundamental particles that we call quarks, and they tend to exist in groups of threes. We won't worry so much about particles called mesons right now, or mesons, which are like a quark and its anti-quark pair. Like I said, we won't worry about that so much. But a proton, you can see, is 2 up quarks and a down quark, and a neutron is 2 down quarks and an up quark. And so these up and down quarks do have fractional charges, so they add up to the familiar charges. For example, we know that a neutron has a charge of 0. And that's because a down quark has a charge of negative 1/3, and an up quark has a charge of positive 2/3. So if you do the math on that, you can see positive 2/3 minus a third minus another third from this down quark gives us our net charge of 0 for a neutron. Whereas if we add up 2 up quarks, we have positive 2/3 plus positive 2/3 is positive 4/3. And then if we subtract away negative 1/3, or we subtract away 1/3, we add up all the charges from these. Let me just restate that. Positive 2/3 from the up quark here plus positive 2/3 from the up quark here is positive 4/3, and then plus negative 1/3 for the down quark is positive 3/3, or just 1, right? And so we get a charge of positive 1 for the proton. Right? And so that's just a simple quark model to describe those. They're made up of those 3 even more what we think of as fundamental particles. Appreciate that electrons and neutrinos are leptons, and so there's another class of fundamental particles called leptons, and electrons and neutrinos belong to that class of particles. So you have, electrons that have a charge of -1, and then there's all these other sort of types of neutrinos over here. Again, really fascinating physics, neutrino physics. The fact that these were predicted before they were discovered, kind of helps to we always have more confidence when we can predict something exists based on a theory, and then observation confirms that to be true, rather than the theorists after an observation trying to sort of find a way to explain it afterwards. All right, and so we can see that quarks here have these charges, and there are 6 different types of quarks: down, strange, bottom, up, charm, and top quarks, and they have the charges that you see here. So up quarks, positive 2/3, and down quarks, negative 1/3, as we talked about, but then these other ones. And it's important that you know the charges of each of these types of quarks. This all, of course, leads to sort of an idea that most physicists would call the standard model of particle physics. And, some people don't like that name. I know that there's a great book called A Beautiful Question, Finding Nature's Deep Design, written by Nobel laureate Frank Wilczek, and he would prefer to call it the core theory rather than the standard model. So this is all part of that sort of particle physics and how we can explain matter in terms of these very fundamental particles. And here's sort of like a table of different particles, quarks and leptons, and then you've also got here the bosons, the weak gauge bosons, the W plus and minus, the Z naught boson. Oh, that's big brush again. So you have the weak gauge bosons. Gluons are that sort of boson that sort of binds the nucleus together, and so hadrons, for example, are particles that interact via the strong force, and leptons do not. And so that's sort of what defines a particle known as a hadron. And then photons, that we've studied previously, you can see the symbol here, gamma, like a gamma photon, like a high energy photon. But that's the particle that sort of governs light. And so each of these particles, we could think about this connected to this grand unified theory. Each of these, boson, these force bosons, what are the fundamental forces in the universe? Electromagnetism, the strong nuclear force, and then the weak nuclear forces that are sort of governed by the weak gauge bosons down here. Gravity is really the other known force, and there is this sort of still theoretical particle called the graviton that you don't see on this table because it's still theoretical. And that just kind of shows you a little bit about how interconnected this physics is to really fundamental ideas and ones that we still have open questions about. So good stuff to research still. All right, moving along here. I'm probably taking too long already, so let's try to wrap this up. I realize that I'm just kind of rushing through a lot of this stuff. If you have any specific questions about anything, please don't hesitate to either leave a comment down below or to, if you're one of my students, send me an email. If you run into a practice calculation or a sample problem that you're having trouble with and you want to request me to make a video about it, I'm more than happy to oblige those requests. Like I said, my goal is to upload worked example questions and conceptual sort of videos aligning to each of the chapters for ACE Physics as a way to sort of supplement my instruction for my ACE Physics courses and my astronomy courses for next year. All right, appreciate that electrons and neutrinos are leptons. I think we already talked about that, but here's yet another sort of chart that shows us what are we looking at here. We got the leptons over here, and so remember that that's electrons and neutrinos are leptons, and then the quarks are sort of that other class of particles that eventually builds up our protons and our neutrons. And together we know that atoms are consisting of things that are made of up and down quarks, the protons and neutrons in the nucleus, and then the electrons. And so it's really looking at the fundamentals of matter really with these learning outcomes here. This chart also shows us that for every particle there is an antiparticle, another sort of taste of the physics to come. We won't get too much into antimatter. Other than that, when we look at these types of radioactive decays, we get byproducts which are neutrinos, or sometimes we get an antineutrino. And so, for example, like there are two types of beta decay. I'm kind of jumping ahead here, but we've got alpha, beta, and gamma decay. And there's beta minus and beta plus decay. And I'll save sort of the details of each of those reactions. I mean, they're in the slides, but I'll go over them in more detail in subsequent videos. I'm just sort of superficially covering the information right now. But I always find it helpful to remember, like with beta decay, if it's beta minus decay, you're emitting a high energy electron. So that's like beta minus because the minus is like the electron that you're emitting. But you also get with that electron an anti-neutrino. So you get this antimatter sort of pair. So you get the regular old, matter, the electron, but you get this anti-neutrino that's emitted along with it. But in beta plus decay, you get positron emission. So you don't emit a negative charge out of the nucleus. You emit, the antimatter sort of component of the electron, the positron. And so when a positron, a positively charged electron, is being emitted out of the nucleus, well, you get kind of this exotic positron, right? This antimatter particle. So you get the boring old neutrino that goes along with that one. So with beta plus and minus decay, you got to kind of remember, all right, what's being emitted, and oh yeah, there's always sort of like this antimatter particle that goes along with sort of the regular old matter that we're used to experiencing most of the time in our universe. We don't have too much interaction with antimatter. All right, let's go on with the slides here. It says, show an understanding of the nature and properties of those types of radiations, alpha, beta, and gamma. And so here's a slide that has sort of like a little experimental setup. It's got a radioactive element in the core here. And there's a lead container so that we're only letting the radiation out sort of one way, then it goes through a series of slits, and then there's plates that are positive and negative. And so the positive plate, well, anything that's negatively charged is going to be attracted that way, right? And so the beta particles, like we mentioned, those are like those electrons, those high energy electrons, because they're negatively charged, they're going to be deflected this way. And so that's one thing that happens to beta particles. They get deflected. They're negatively charged. They're electrons. Gamma particles, gamma rays, those are just light. It's high energy light, gamma photons. And so they're not charged, they're not deflected by this electric field right here, by this, positive and this negative plate. The alpha particles, they're deflected, but a small deflection because they're more massive. Okay, you've got a helium nucleus, so 2 protons and 2 neutrons, so it has a nuclei number of 4, whereas this is just an electron. And so an electron has a mass of 9.11 by 10 to the negative 31, which is many orders of magnitude less massive and therefore less inertia than something like an alpha particle, which has high mass, high inertia, and so it's not deflected as much by the electric field that exists between these plates right here. Pop quiz. Told you when you least expected it. what would be the direction of this electric field right here that's deflecting these particles? Well, remember the rule, how would a proton move? And so if there's a positive plate up here, a proton would be repelled by it, and so a proton would move like that. So the direction of this electric field is pointing down. Good job. All right, so once again, if you send these particles, there's some radioactive sample that's emitting alpha, beta, and gamma, sort of all these radiations at once. So, how could we separate them and sort of tell that they're different? Well, one's going to be deflected a lot, the beta particles in one direction, the alpha particles, because they're positive, they're just the protons, the neutrons aren't charged, so it's the nucleus of the helium atom, so there's two positive charges in this alpha particle. So oppositely charged is the beta particle, the electron, and then the gamma light, the photon. The gamma photon is not charged. So this is kind of just showing us the same thing, although this time we're looking at a magnetic field that goes into the page there. I did say up here that this was an electric field here, right? And so we could kind of think about the charges on these things being deflected by an electric field. But students that haven't studied sort of the relationship between electricity and magnetism, when we have an electric field, we also have a magnetic field. Show an understanding of the nature and properties of alpha, beta, and gamma radiations. All right, so we're still looking at this learning objective. Here we see like just a picture of a nucleus here, and we see here's this alpha particle being radiated over here. So it's the helium nucleus, the two protons and neutrons. So that's that guy over there. We got our high energy electron, that's our beta decay. And so at the same time we would get this electron, this, sometimes we'll show this like a beta minus, this electron like this. We also get this is the symbol here, nu, for a neutrino. And the antiparticle gets this bar over top of it. Sometimes we'll use the subscript E to denote it's an electron neutrino. As we saw in the other slides, there are different types of neutrinos. And then gamma radiation is just a photon, right? And so here you're sort of seeing like this oscillating electric and magnetic field that we know light is, and so that's just gamma radiation. There are three types of radioactive decay. So this picture here kind of summarizes them all. Right. Show an understanding of, so same learning outcome. This is sort of about, if we go all the way back up to the, I think it was the Florida standard. That's also, related to the ACE learning outcomes, but here where they say compare their properties, the three types of radioactive decay. So now we're, once again with that. So now we're looking at sort of this piece of the standard, right, and where they clearly overlap alpha, beta, and gamma decay, and it says their composition, their mass, their charge, kind of talked about each of those, and the penetrating power, right? What do they mean by that? And so that's kind of where we're at right now. All right, and so we can see gamma radiation kind of makes it through everything, even, thick lead or concrete. I suppose if we're infinitely thick, then it could absorb all gamma radiation, but, a pretty thick sheet of lead will, for all intents and purposes, absorb most of the gamma photons. I suppose some still theoretically could get through. You can see that aluminum will absorb beta particles. So electrons can be absorbed by aluminum. You can see it's 2 to 3 millimeters in thickness. And skin or paper can actually absorb alpha particles. All right. So that's sort of their penetrating power. How far can they get in? And I'll sort of explain this in a little bit more detail also in a subsequent video. Sort of why do they have this? But for now, let's just sort of accept this as true, that each of these things have different sort of penetrating power. And this slide kind of show what that is for each one of them. So again, gamma makes it through everything. You can see even there's a little bit of gamma radiation still making it through the lead, whereas aluminum would stop the beta decay, but beta particles could make it through something like paper, or they show up their skin. but alpha particles would be absorbed by something like paper. Okay, like I said, we'll talk about more about the reason why that's true in a subsequent video. For alpha decay, the next couple of slides just kind of have the very similar to chemistry, how we would just sort of keep track of all of the nucleons are conserved, for example, that mass, energy is conserved. So it's just a way to kind of write out sort of what we've got. For alpha decay, we've got some unstable atom that's going to emit this alpha particle over here. And so what's going to be true about this sort of more stable atom, this daughter nucleus? Well, it's going to always have a number up here, the nucleon number, that's going to be 4 less, right? Because we got 4 of them went off in this helium nucleus. And the proton number is always going to decrease by 2 because there's 2 positive charges in this alpha particle. And so that's going to always be true. When an unstable atom emits alpha particles, then the new sort of daughter nucleon will have a nucleon number that is 4 less than it started with and a proton number that is 2 less. That's alpha decay, sort of the math / radioactive decay equation for alpha decay in general. All right, so you can see there that I've highlighted sort of the alpha there for that slide. And there's plenty of worked example questions that I'll be uploading that focus on each one of these in the weeks to come. Take your time. Remember, that's another thing, students. You don't got to rush through this. Sometimes we need to take our time with these learning objectives to make sure we're really understanding them. All right, here we see the examples of beta minus and beta plus decay that I kind of mentioned a little bit earlier. So here they've got carbon 14, right? That isotope that we know is unstable that they mentioned earlier. So one of the ways it's going to decay is it's going to emit this beta particle. And so when it emits a beta minus particle, look what happens to the proton number. It increases. And so it's sort of like a neutron inside of the nucleus. It's not the best way to think about it, but it's maybe helpful in terms of keeping track of the charges. So this neutral nucleus had like a positive and a negative charge, and it sends out the negative charge. And so what's left behind is like the positive. So you can see that the proton number increases. It goes up by 1 because it's sort of like that neutron turned into a proton, okay? So the neutron number goes down, but the proton number goes up, thereby conserving the nucleon number. We don't lose any nucleons in the nucleus. It's just a neutron becomes a proton. And so we can kind of see that, with these numbers like this. Right, so a neutron became a proton. And that's why the proton number went up, and that's why the neutron number went down. In so doing, we emit this antineutrino and this electron. Remember earlier I said it's kind of cool how if you get a regular old electron, regular old matter, electrons and all the atoms, you get a cool antineutrino, antiparticle. Cool. But down here in this beta plus decay, well, then you're emitting a positron. So that's the antiparticle of the electron. It's a positively charged electron, positron. So whenever that's emitted in beta plus decay, you get a neutrino, not an antineutrino. So you don't get 2 antimatter particles together. You always get one sort of antimatter particle with a regular old matter particle. So in beta plus decay, we're emitting that positron, that beta plus particle. So here the beta particle is this, and it's like an electron, but it's its antimatter sort of counterpart. We call it a positron. And so kind of look what's happening with the proton and neutron number there. There, a proton is becoming a neutron. So the proton number decreases. Okay, so we can kind of think about it as we had a proton that kind of like kicked out its positive charge in the positron and it transmuted into a neutron. And so the neutron number increases because one of those protons just became a neutron, and the proton number goes down. And because we define the chemical species by the number of protons, you can see in each one of these types of beta decay, we're transmuting to a new chemical species. So carbon 14 becomes nitrogen 14. We didn't change the number of nucleons, but we did change, because we changed the number of protons, we swapped a neutron for a proton in beta minus decay. We changed carbon 14 to nitrogen. So we went up on the periodic table, right? We increased the proton number. Here, though, this carbon-10, okay, so this unstable isotope of carbon-10, I don't know, it might be on that chart that we had earlier, it's going to transmute into boron-10. So again, it doesn't change its nucleon number. It still has 10 nucleons, but now only 5 of them are protons, and so it's boron. So it went sort of to the left on the periodic table. Carbon went back to boron there, right? And when we're kicking out a positive charge there, the positron, we're just getting the, because it's an type of antimatter, we just get the neutrino, which is a type of matter. So there's beta decay. And I think we're getting close to the end here. We got gamma decay, and says we have some excited sort of nuclear state for some parent cell, and then it sends out a gamma photon, and then we get a more stable daughter cell. So here is an example of like carbon doing this, carbon 12, kicking out a high energy gamma photon. So gamma rays are emitted in nuclear processes, and so, for example, the gamma photons in like the core of the sun, so there's nuclear fusion that's occurring in the center of the sun. Speaking of fusion, this graph right here, this is just some data, and maybe goes beyond the scope of both the learning objectives related to the ACE physics course and the physics honors, but I think it's really important. Okay, so here's some data, and it's just a plot that's showing the number of nucleons in a nucleus. So it goes up from like 0 or 1 hydrogen, 2 helium, lithium. So it kind of goes through the periodic table here all the way up to like uranium 238 here. And it's got the average binding energy per nucleon on the y-axis. And so that's kind of confusing, but it's basically saying like how much energy does it take to keep these nucleons bound together in the nucleus. Remember that protons are both positively charged, and so it takes a strong force, right? And that's the idea of, the weak gauge force, the boson, the gluons that glue the nucleus together. And so how much sort of energy does it cost us to bind that together? All right. And that's what they're showing here on the y-axis. In the slides, I say the shape of this graph is really important for like pretty much everything in our universe. Try to think about why. And then I thought, I should maybe make a video and just kind of explain some of these slides. So the shape of this graph is really important. And I don't want to give you too much because, like I said, it's kind of beyond the scope of this course. But you can see, let's just look at sort of what the slide sort of shows us here. It's saying fission kind of goes that way with our, once again, thick pen there. All right, so we've got fission that kind of moves this way and fusion kind of moving that way from where? This peak at iron. All right, and I think I even say in the slide down here that iron at the peak means it is the most stable element. So there's like one hint there. So iron is the most stable element. All of these elements that are sort of heavier than iron, they can be stable, but they'd be more stable if they could fission, if they could split apart to iron. So we get energy out of these things by sort of fissioning them to iron. Here, like the sun is getting energy by taking hydrogen here, and it's fusing it with another sort of hydrogen to make, eventually helium. And then eventually our sun will fuse that, helium into carbon and oxygen and so on. But right now you can see that there's some energy to be had by fusing hydrogen atoms into helium. Okay. And so sort of the difference in the energy here kind of gives us like an energy budget for the energy that could be got out of, fusion reactions or fission reactions. And there is a connection, by sort of looking at the data in a plot like this, it would help us make sense of that standard, which specifically mentions, fusion and fission. So fission is splitting apart atoms, and fusion is putting together atoms or nucleons to make, bigger atoms. And the when we do that, like if we put together two hydrogen atoms, we get helium, but that helium is going to weigh a little bit less or have a mass that's a little bit less than the mass of the hydrogens together. And so that mass defect, we say that tiny difference in mass, is related to energy by Einstein's famous equation E equals mc squared. And so that's really sort of what's the connection here. That's really profound, and that I'll probably make a separate video on talking about Einstein, but that the relationship between energy, a concept that we've been studying throughout physics this year, so both in mechanics and looking at the energy of motion and kinetic energy, to looking at electrical energy, to seeing how waves carry energy. There was a cool song, I think, Waves Carry Energy. Check that one out if you want to. And now we see how matter and energy are really two sides of the same coin with Einstein's famous E equals mc squared. So that seems like as good a place as any to leave it. Again, if you guys have any questions about anything, please don't hesitate to reach out to me. I'm here to help. And um, again, just use this as an opportunity to do something that you want to do. If you feel like learning physics, you've made it this far, then keep learning physics. If you don't want to, then don't stress yourself out over it. This should be an opportunity for you to explore how do you learn best for yourself, a chance to think about your thinking and metacognition. And so even if it's not physics, what is a cool project that you'd like to really research and to do something that's worth your time? That's what I encourage you to do right now. So I thank you all for watching and for doing your work, and I'll see you next time.